All right, so let's continue and look at our lab number 4. And in the previous lab, we had seen RC and RLC circuits, and we had seen one particular application of those particular circuits in the field of filtering of noise. And in this particular lab, we look at another application of both RC circuits and RLC circuits, and that's for construction of oscillators. And so oscillators are used in many applications. For example, the entire communications, when you want to send a signal from one place to the other, and the entire communications relies on an oscillator being present. When we are talking about oscillator, we are talking about a circuit which will produce, in this particular case, a sinusoidal signal of a particular frequency. So there is no input to the circuit except for DC, and the circuit generates a sinusoidal signal of a particular frequency, right? So we mean, when we talk about oscillators, we are talking about sinusoidal oscillators here. And so, as I said, in communications, oscillators are used to generate a modulated signal which is transmitted over long distances. And in many other places, for example, if you have an electric guitar or a piano, they all require sinusoidal oscillators, and there are many other applications as well. So these oscillators are built by using, in the most common way, they're built by using an amplifier. So this triangle here shows an amplifier, and they're built by applying what we call as a positive feedback. So feedback, first of all, understand that here is an amplifier, there is an input to the amplifier, and there's an output here. So feedback is when we take the output and multiply it by some factor here and feed it back to the input here, right? So some part of the output is fed back to the input here. So then we say the amplifier has feedback in it. And here we are specifically talking about positive feedback, all right? And for example, if you look at this particular picture here, so we are taking output here. We are taking output, multiplying, there's a circuit here, which we will see. There's a circuit here, so that multiplies it by a factor called, let's say, beta f, feedback factor here. And you generate a output here. At this particular point, the output will be V0 multiplied by beta f, and that is fed back to the input here. So the input to the amplifier then will be equal to the original input V in plus the feedback signal, which is nothing but beta f times V0 here. And this signal is then amplified by this gain here, A0L, and will generate V0. So on the basis of that, note that this amplifier, without feedback, you would just give an input here and you'll take the output here. So in that case, we call this particular amplifier in open loop configuration here. That's why the word OL here, open loop. Now with this amplifier, with the feedback present here, the input is here, and the output is here, and so V0 by V in, we call it as a closed loop gain here, closed loop. So it's this original amplifier along with the feedback loop here. So we call this as the closed loop gain here, so V0 by V in. And it's very easy for you to show based on what we have just discussed, that the closed loop gain is equal to open loop gain divided by 1 minus open loop gain times the feedback factor beta f here. Now what we note interesting here is that if we make this particular factor, open loop gain multiplied by beta f, if we make this particular factor equal to 1, then the denominator goes to 0 and the open loop gain goes to infinity. So that's the condition for oscillation, that if we have a small disturbance in the circuit, then that particular disturbance will then get infinitely multiplied. And under certain conditions, because the gain of the amplifier doesn't remain constant with the amplitude, so eventually we will see in simulation you begin to get sustained oscillation here, especially if you arrange that this particular factor is equal to 1 for a single frequency. For other frequencies, the factor has, the magnitude of this particular one can be different from 1, and the phase is also different from. Right now, when we say equal to 1, we mean the magnitude is 1 and the phase of this whole quantity is 0. Now at some other frequencies, the phase may not be equal to 0 and the magnitude may be different from 1, and therefore the oscillation will not occur. Now the purpose, when we want a sinusoidal oscillator, which basically means that the circuit is oscillating at one single frequency. We want to arrange that this factor, this condition is satisfied at one single frequency. If we can ensure that, then the gain will go to infinity for that single frequency and oscillations will occur for that particular frequency only. All right, so that's the background that we need to understand how to construct an oscillator using an amplifier. So you need an amplifier and then you need to create a feedback network here, right? Okay, so the first oscillator that we will look at is what we call as an RC phase shift oscillator. So let's go to the simulator. All right, so this is the simulator that we have here. Now note that if we go back here, if we look at this particular picture, what we need is a amplifier and we need is a feedback network, right? The feedback network here. So what we are showing now is a feedback network that you see here. This is a feedback network, right? So, so the input to the feedback network is here, right? So this is the input to the feedback network and the output is over here, okay? So the output is taken here and this is the output here, the V feedback signal here. So this is the network that we are talking about. Why are we using an RC network? Because we want to remember for oscillation to occur, we just said that this condition needs to be satisfied, which means that the net phase should be 0 and the magnitude should be equal to 1 here. So that's what we need to do. So this RC circuit will give us a phase difference between the output here and the input here equal to 0 at one single frequency. At all other frequencies, the phase will be different from 0 here. And therefore, if we now take this feedback network, we will show you and attach it to an amplifier. So what kind of an amplifier we are thinking of? An amplifier which is a op-amp based amplifier here, right? So you've all studied that if you take an op-amp, it has an inverting and a non-inverting terminal, and if you connect a resistor here and a connector resistor here, then this is an inverting amplifier where the gain between the input and the output is the ratio of these two quantities here, R19 by R20 here, and a phase difference of 180 degree, right? So we will use if we double click on this, we will use an op-amp called LM741, right? LM741, and make sure that the level is 3. You use the right model for this particular op-amp here. So it's a very common op-amp IC which is commonly available in the lab. So we'll use that particular one. So LM741 is the one that you have to use here. And as I said, level 3 here. All right. So this is the amplifier that we will use. This is the amplifier that we will use. And this is the feedback network that we will use, right? And we'll join them together to create an oscillator. So before that, let's study the feedback network. So what is the goal of the feedback network? Again, remember, the input to the feedback network is here, and obviously the output is here. So let's look at this feedback network and do an AC simulation, right? And look at the behavior of this output here, right? So let's look at the node here. So this is node number 4, right? So node number 4, let's do an AC analysis. And we're going to look at node number 4. All right, so we'll look at node number 4. Let's disable this, enable it here, enable it here. So we'll look at the amplitude of V4, the output, and the phase of V4. All right, so we'll look at both of them here over a range of 10 kilohertz to 100 hertz here. So let's look at that. Right, so this is how it looks. So let's look at the phase part here. We can use a cursor and look at the phase. So the phase is, you can see here, minus 115, and the phase is changing here, right? Okay, so the phase is changing here. Now we are specifically looking for a frequency where the phase is 180 degrees here. I'll just explain in a minute why 180 degree here. So 180 degree phase occurs at 650 hertz here. So 180 degree phase shift. And at that particular point, the amplitude, output amplitude is 34.575. Note that when you do AC analysis, the input by default is 1, right? So the input is 1 and the output is 34.575 millivolt here. So what does it mean? It means that at that particular frequency, the ratio of the feedback voltage to the input voltage is 34 millivolt here, and the phase difference is 180 degree. Now, why are we doing 180 degree? Well, if you look at this amplifier, there is a phase difference of 180 degree already here, right? Between the input, we said the output divided by input is minus of R19 by R20. So there's a 180 degree phase shift here, right? So if we go back to this particular condition, this condition is that A0L times beta F equal to 1. So A0L already has a minus 1 into it, right? Minus 1 into it, 180 degree phase shift, which means it has a minus sign with it. And therefore, to create a positive sign here, we need a minus sign here in the feedback network, which means 180 degree phase shift. All right, it's for that reason that we are looking for a frequency here where there's 180 degree phase shift here. Right, so at 650 hertz, we have a 180 degree phase shift. So at that frequency, it can oscillate, but the output is 34.575 millivolt here. Right, so the other thing that we need to bother about is the magnitude of beta F. So we have taken care of the signs. This is minus, and minus will give us plus. But beta F was 34 go and look at it again, 34.575 milli, right? So it's milli here, 34.575 milli. So we'll have to multiply it by a gain, which will be inverse of 34.575 milli, which is around, I think, 29 or so. So we'll have to multiply by that much gain in order to get a gain of 1. All right, so that's how we will construct an oscillator here. We'll take this feedback network. So note that this input, this we will connect it here now at the output of the amplifier here. And this part that you see here, we'll connect it to the input here, right? This is the feedback signal here. And so this particular CR network, RC network that you see here, produces a 180 degree phase shift, again 180 degree phase shift at around 650 hertz here. And so how do we construct an oscillator then? So that's the first part that you need to study. You need to study the phase response and the phase and the magnitude of this particular feedback network here. All right, so keep in mind that this is a feedback network that we are using it with this amplifier here. So how do we connect this circuit here? So this is what is shown here, right? So note that this is the feedback network. This is the feedback network in red. The output is taken here, and this is how we sum it up. So this is the original amplifier. Original amplifier is shown here in blue and green here, and this is the feedback network here. Note that in this we need to add them up, right? Adding up the original signal and this signal is added up. So this is how we simply feed it through an R here, which is a part of this RC network earlier here, and that helps us to add. So whatever is the signal here, it gets added to the amplifier here and gets amplified. Right, so this is our amplifier now with a feedback like this here. So what we discussed was that if your condition is right, if you go back and look at this condition here, if your condition is right, then A0L beta F equal to 1, which means that since beta, the value was small in millivolts, so A will have to be compensate for that small value here. If that condition is satisfied, then the closed loop gain V0 by V in will tend towards almost infinity or very large value here. So that's what we would like to see here. So let's come out of this AC analysis and let's go towards this feedback here, right? So this is the amplifier now, original amplifier, inverting amplifier with this feedback added to it. Okay, so let's look at the node. We want to see the output here, V7. And so let's do the AC analysis. And we have put a gain here. Let me put a gain initially when the gain is not enough, say 20. Or even let's put it a gain of 10, right? So gain of 10. And let's look at V7 output, okay? Analysis AC, and V7 is here. So we disable these quantities here, enable it here, and let's look at it here. So you can see that at that particular frequency at which the phase was falling to here, so there is a there is a peak here at this particular point here. All right, at this particular point. So let's increase the gain of the amplifier here. So this is 10. So note that the normal gain, if there had been no feedback, the gain of the amplifier should have been 10. Why 10? Because this is 10K and this is 1K. So without feedback, the gain should have been 10. Right? So that's what we see, gain is 10 when there's not much effect of feedback. But then at that particular frequency, at a certain frequency, the gain is increasing to almost 22 or so. But right now it's not been designed properly here. So let's increase the gain to 20. Let's see what happens here. So note that the gain has increased to, from a value of smaller value to a value which is much higher here, right? So now the gain is 114 at a frequency of 745, but still we have not satisfied that condition, right? So let me put here which is very close to that particular condition, 29.5 here, which is 1 over 34.5 whatever millivolts was there here. So let's look at, now see the value of the gain here. The gain is going towards almost like 3000. So gain is tending towards infinity. So that's what we said. If you choose the condition properly here, if you choose this condition properly here, A0 L beta, if you make it equal to 1, the closed loop gain, V0 by Vn, will tend towards infinity. So that's what is happening here. The gain is going. And at what frequency is it going? Well, let's see. Note that is at very close to that particular frequency of 640. I think what was the frequency there? Around this particular point only we saw that the phase was equal to 180 degree here. Right? So what we are saying is that now with this feedback here, now this particular amplifier, the closed loop gain is going towards infinity here. So in an oscillator, what we do is we don't apply any input. No input is applied, but the circuit is shown like this here. So this is the oscillator, right? There is no input applied. So we remove the input part here, and any small disturbance in the circuit will get amplified, and it will generate the oscillations that is there. So when you switch on this particular circuit, there is some disturbance, and in that particular disturbance, one particular frequency is selected, and that gets amplified, and you start getting oscillations here. So before that, I want to show you the same circuit here, right, with feedback, and I want to apply a small narrow pulse. Okay, so look at this pulse here. So if you look at this, the pulse is from 0 to 0.1 volt, and you know, it's a narrow pulse with a time period of pulse width of 1 microsecond, right? So a kind of a disturbance to the circuit here. So it's only there for 1 microsecond. After that, it's not there, okay? Because the period is 1 second, so it will be 0 for a long time, and we are not going to carry out simulation till 1 second. So we'll, you know, so a narrow pulse of 1 microsecond, amplitude of 0.1. So see what happens here. So we'll do transient simulation. We'll look at output as 18, V18. So let's come out of exit analysis here, transient, and we'll look at V18, okay? V18 here, and we are simulating it for, let's say, 40 milliseconds. See what happens here. This is what we, you know, that was a very narrow pulse right in the beginning here. So as a result of this, see this disturbance which is growing here, right? And after a while, you know, the op-amp really saturates, it doesn't grow anymore. So it's constant. You can see the op-amp saturating here. The op-amp is saturated here and saturated here. Right, so many times what we do is we add a some kind of a circuit here to prevent, you know, in parallel to it, to prevent it from the op-amp going into saturation and to give us a cleaner or a better sinusoid. But you can see what is happening is that the signal is growing. On the other hand, if the gain is not enough, if that oscillation condition is not satisfied, you can see that the signal will not grow. Suppose I put 20 here. Note that the oscillations die down because the oscillation condition is not satisfied. So any disturbance actually dies down. On the other hand, the moment I make it, let's say 30 here, note that the oscillations, we get a sustained oscillation. If we make a little larger than that, say 35, note that we have a growing oscillation here. right? So it all depends on how much gain you build in here. And once you build in enough gain, any disturbance in the circuit will get will get amplified at the frequency at which this positive feedback is occurring, right? So that only, note that only that particular frequency is getting amplified like this here. So finally, as I said, to make an oscillator, what we do is we remove this input here. In an oscillator, there is no input and there's only DC. And the moment you switch it on, then this circuit starts oscillating here. So this is our oscillator circuit here. No sinusoidal input, no pulse input, nothing is there except for DC. The op amp has some DC supply voltages, that's all there is, right? And so let's look at V13, transient analysis limits V13. So we'll look at that. So note that an oscillation occurs here. An oscillation is growing here, so it's not reached steady state here, but an oscillation is occurring. On the other hand, if I don't have enough gain, suppose we put here 20K, note no oscillation, it's flat, right? There is no, except for, you know, when you switch on the circuit, so there's a disturbance, but it dies down and there's nothing here. So you need a minimum gain after which the oscillation builds up here, right? So that was around 29.5. So let's put a gain of larger, let's say 35K here. So note that the oscillation is building up here. Okay. All right. So, you know, so this is the oscillator that is there here. And so what you can do is you can study, first of all, the phase response of this particular circuit here. So the goal is to generate 180-degree phase shift, and note the amplitude of the voltage here. This amplitude is 1, so note the amplitude. So this circuit actually gives you an attenuation factor, and then we have to ensure that this condition is satisfied at that particular frequency here, right? So we choose gain, which is 1 over whatever is the value of the voltage at this particular node here. And once we ensure that, then you can look at a circuit like this, and you can see that if you look at his AC response, you can see that the gain goes to starts to go to infinity. And then you can make a oscillator, a circuit like this, an oscillator, and see that it actually oscillates with the right values of the gain and at the frequency at which the phase of this particular part was going towards 180 degree here. All right, so that's part 1 of this particular oscillator. So now what we did was, based on this, we designed a oscillator, the oscillator that is shown over here, and we asked this person in a lab to take a 741 op amp and construct that particular circuit here. So I'm just going to show you that circuit. By the way, you have to design it for a frequency of 2 kilohertz. So I'm showing you a design here. So the person designed, so this was the circuit that was there here, right? With CER, CR and all that you see, an op amp, and with this original this amplifier. And this is where the feedback signal is. So the circuit was made on breadboard here. So this is the medium on which we normally, you know, when you want to quickly evaluate circuits, so you can very quickly construct circuits here. So breadboard here, so note that you have these holes that you see here. So all these, underneath all these holes, they are connected together here. So you can put in components, like you see a resistor here, capacitor here, and this is our op amp. So you can put a component in these holes, and all these holes in a row, in a column like this, they are shorted together. But this one, these are also shorted together, but then this is isolated from this particular one here. So there are all these holes that are there here where you can plug, you know, insert your component that is there here. This line here that you see here, this particular line, in this case, the row here that you see here, all the holes are shorted together in this particular row. And all the holes are shorted together in this particular row, but this row is isolated from this particular row here, right? In this case, all of them in a column are shorted together, but one column is isolated from the other, right? So see how the circuit is made here. This is our op amp here, 741 op amp here. So it's a 8-pin IC here, 1, 2, 3, 4, 5, 6, 7, 8 pin IC here. And these are the resistors you can see here. The first capacitor here is this one. Then there is a resistor R1, which is here. Then the second capacitor, and then the resistor R2. Then the third capacitor here. Then this particular resistor is connected to the op-amp input here, the inverting input here, minus, which is over here. So you can see this particular resistor is connected to this particular here. From this particular part here, you can see that the resistor is connected to the capacitor. Okay, now these resistor, one end is ground, so one end is connected here, the other end is over here, and all this row is a row which is ground here, right? It's connected to the ground terminal here, so that's why these capacitors are coming to the ground here. And op-amp has a supply voltage, so negative supply voltage is here given to this particular terminal, positive supply voltage is given here to this particular pin here, and the op-amp's output here is at this particular node here, right? This particular node which is connected to C1 also here. So this output node is connected to the oscilloscope. So we connected it to the oscilloscope where we monitor the signal here. So this is our oscilloscope here. And this is where we connect, it is a 2-channel oscilloscope, which means you can see 2 waveforms simultaneously. So we connect the input here, and then we can see the waveform. We can look at its amplitude and frequency and all that here. This is our power supply. You can apply, you can get plus minus 12 volt and all that from this particular power supply here. Right, so this is what we get when we made this particular circuit here, right? When we made this circuit here and we looked at it on the oscilloscope here, the output here at this particular point is what we see on the oscilloscope here. The oscillator is working, and it gave us a frequency of 642 kilohertz, which was about 10% off from simulation gave 642 kilohertz, while the actual measured frequency you can see here 716 hertz here. The peak to peak amplitude, so it's going from the scale is 5 volt, I think. The scale is 5 volts, so it's going from about plus 10 to minus 10 here. So those are the op-amp almost like saturation voltages here. And 642 kilohertz simulation gave, and the actual frequency is 716 hertz here. So it's about 10% off, which is kind of expected because the resistor values will not be exact. The capacitor values also have a tolerance. So this much error we expect between simulation and experiment. All right, so just to show you that the circuit that you would design, and if you, the whole circuit doesn't take too much time to breadboard and works very close to what we get from simulation. So in part A, what we want you to do is study this RC phase shift. This is a phase shifter. The goal is to provide 180 degree phase shift. This is our inverting amplifier, and using a 741 op-amp, and connect them together and construct an oscillator. Now in your case, you have to choose RC network such that the phase shift is 180 degree at 2 kilohertz. Right, so you have to just tune the value of R here. So make all the R's the same, make all the C's same, and tune the value of R to get a 180 degree phase shift at 2 kilohertz. Then connect this up with a suitable value of gain here. You will see that for smaller gains the circuit will not oscillate, but for larger values of gain the circuit will oscillate. All right, there's a minimum gain above which the circuit will begin to oscillate. All right, so construct this RC phase shift oscillator. In the next part, we'll look at another way of constructing an oscillator, which we call as a Wien bridge oscillator. So let's look at that. By the way, for the oscillator to work, please make sure that when you do transient simulation, just disable the operating point. Don't tick the operating point, because if you tick the operating point, then it will settle down in an equilibrium state and it may not oscillate at all. Okay, so don't do that. All right, so for example, let's say if I switch on the operating point, let's see what happens here. All right, so note that there's actually no oscillation, 4.18 milli. So the whole scale is 4.18 milli. There's no growing. So it will not simulate properly. So disable the operating point, just do auto scale and run it, and then you should see the oscillation occurring here. So that's what we call as a phase shift oscillator. In the next case, let's look at what we call as a Wien bridge oscillator. So in a Wien bridge oscillator, we have a different kind of a network here, feedback network here. So the feedback network consists of an RC network here, series RC, and then a parallel RC. Now this circuit is interesting, so this is the output here. This is the feedback value here. So we can change it to we can call it V feedback here. This is the output here, V feedback signal here. All right. Okay, so this is the feedback output here that we feed in here. Now this circuit is interesting because if you look at this simple RC here, series RC, that will have a phase of -90 at low frequencies, and it will go, when you go to very high frequencies, the capacitor will become a short and you'll get a resistor. So the phase of this goes from -90 to 0, this part here. On the other hand, if you look at the parallel RC, at low frequencies the capacitor is like an open, so the phase is 0. But at high frequencies the capacitor is dominant in parallel and the phase goes to us -90. So the phase of this is going from -90 to 0, while the phase of this is going from 0 to -90. So there is one point at which the two phases will intersect, which means that the output here will be in phase with Vs. So in this case, the amplifier that we will, the oscillator that we will construct is that we will use a non-inverting amplifier. So it is a plus here. It doesn't have a minus here. And therefore, it's a plus here, so we need a plus here, which means a 0 phase here. So what we are looking for from this particular circuit is a frequency at which the phase shift between the input and the between the output and the input is 0. And this is the frequency at which, if we use a suitable gain here, the circuit will oscillate here. So what we'll show you is, let's do an analysis. Let's look at V3 AC analysis, and we are looking at V3. All right, V3, both amplitude and phase, and let's look at it here. Right, it goes like that. And let's look at the phase part here. So there would be a phase of note that at this phase of 0 here, right, at this part here, almost phase of 0 here at 1.58 kilohertz here. The phase of the circuit is 0. The gain at this particular point, if you look at the gain at this particular point, is 333 milli here, right? So which means basically that the signal is getting attenuated. So this particular circuit here will produce a 0 phase at that 1.58 kilohertz, and the output is 0.333, right? So this is what the circuit does. And to construct a oscillator, this is what we do. We have a non-inverting amplifier here. Note that this is the input here, non-inverting amplifier, and we connect the output here to this non-inverting amplifier, right? So there is no input, a non-inverting amplifier with a certain gain, and the feedback signal is fed back to the non-inverting terminal here. So this produces a 0 phase, and the amplifier between this node and this node is also 0 phase here because it's a non-inverting amplifier, right? So this is what we call as a Wien bridge oscillator. And by basically, by basically looking at by using, so use C1 basically equal to C2 and R1 equal to R2 in a simplified design. And by adjusting the value of R and C, you can tune the frequency at which you get 0 phase, right? And that's the frequency at which the oscillator will work here, right? So we can see this particular oscillator again. You can go back and look at node number 7. So if you do, let's say analysis, if you, go back here to the oscillator here and do analysis transient at node 7. Node 7, let's say here. Let's see what happens here. Right, so this is also oscillating, you can see here. Node 7 here is the output and it's oscillating. Now if I don't have enough gain here, so suppose I put 1.8. We don't get any oscillation here. Note the scale is simply 2.87. So we are seeing that you need a certain minimum gain for this to work. 2.1 here. Let's say we put here, and then 2.1. All right, 2.2. 2.2 here. right? So this is oscillating. Let's zoom here, right? So the op amp is really saturated here, and we can look at the frequency. The peak value is here. Let's look at another here. So we can see the difference between these two is left and right. The time period is about 614 microsecond here. So if you take 1 over this, it will give you the frequency here, the frequency at which the oscillator is working, and you can compare it to your earlier analysis of where the phase was going to 0 and see whether it tallies with what you get here. So this is called a Wien bridge oscillator, and Wien bridge oscillator is there. So the other thing that we can do is we can construct another oscillator, which is what we call as a Hartley oscillator. So these are all based on the same principle. So in this case, what we are using is an LCR circuit here. So we have a capacitor, we have an inductor, and we have another inductor here, and inductor here, and then resistor here. So in this case, so the basic idea in this particular case is to produce, note that what we are going to use is an oscillator. We're going to feed it into a inverting side here. So the amplifier has 180-degree phase shift. So what you're looking for is, this is the output here. This is where the feedback signal is, okay? There's a feedback signal here. So what you're looking for is a phase difference between this node and this node of basically 180 degree. So you're looking for 180 degree phase shift between these two nodes, and then you take this particular feedback network that you see here and construct an oscillator. So note that this is the resistor here, this is the inductor, capacitor here, and this part here is connected here. So when you take a node and name them as Vout1 and Vout1, microcap will automatically connect those particular nodes here. So instead of actually taking a wire, you can name a node as the same node here. So it will assign is same as connecting them with the wire here. So this node is connected here. So this provides 180 degree phase shift, and this particular network will provide 180 degree phase shift here. And if you choose the gain properly, then the oscillator should give you the oscillation. So this is based on a LCR network. And so the basic idea behind this is the way it generates 180 degree phase shift is as follows. So there would be a certain frequency at which this L, C, and L will oscillate, and a parallel resonance. So at that particular frequency where L, C, and L, forget about this is a large resistor, so let's not look at the influence here. So this will go into parallel resonance, and in parallel resonance this particular circuit will act like a open circuit, or very, very high impedance, so open circuit. So what happens is whatever signal you apply here, the same signal will appear at this particular node, which means that you get a 0 degree phase shift at this particular point here. Now at this point here, C and L, you can easily see that at the output here, then there would be 180 degree phase shift between this and this particular node here, right? Because when you have only a C and a L, forget about R for a moment, then you get a 180 degree phase shift between this and this particular node here, right? So that's how you generate a 180 degree phase shift, and you can look at, if you wish, you can derive easily the expression at which the parallel resonance occurs, because that's the frequency at which the oscillator will occur. So basically, which means that the impedance of this whole point here, this L2, C1, and L1, without this resistor being there, the impedance goes to infinity. So that's the condition for parallel resonance, and that's the frequency at which basically you will get a 180 degree phase shift at this particular point. And of course you'll get some gain between these 2 points, and that particular aspect is also taken care by the gain of the amplifier, right? So we have a amplifier gain also, which can adjust for any attenuation of the signal from here to here. So that part is compensated for the gain of the amplifier here. So so the main thing that you have to do is explore the simulator to analyze and design three kinds of oscillators: RC phase shift oscillator, then Vein bridge oscillator, which is also an RC network, and then finally a Hartley oscillator based on an LC network here. All right, so let's stop here.